in chapter 6, what we're going to do, we're going to go through three different sets of instructions. Okay. And then I'll tell you more about the formats. And the second part of the chapter 6 will turn each instruction into machine language. So last time we talked about LDR and STR. In the instructions, the first register is going to be our destination register all the time except one for STR. So this one is loading to register from where? Memory. These are the two instructions. I mean, later we're going to talk about, we'll have a B right next to it. It's a byte address, but kind of taking as a byte. But mainly we're looking at LDR and STR, okay? So LDR and STR, those are the only two instructions we're gonna deal with the main memory. LDR, we wanna get into main memory, take that information into register. So let's say, as an example, we have R1 as its OX04. So now we need to go read the main memory, and memory address what? 4 plus 12, which is 16. It is hexadecimal, it's a 16. And read the contents. 2, 3, 4, 1, 2, 3. Store into R1. After this, we're going to have R0 equals 0x, 1, 2, 3, 4 is 1, 2, 3. Make sense? So here's the two things. LDR, STR, we need to access to the memory. LDR, we're going into memory, take it the contents of memory, put it into register. STR, initially we said STR as OX0001. We're going to store this into main memory, where R1 as a 4 minus 4, very bottom, is a 0, 0. That's the location we want to store this guy into. I mean, initially we say this. Now we're going to replace this guy as, so STR is the only instruction. I said only for now. I mean, later, we have some another exceptions, but only instruction, the first register is source register. Read the content of R0, store into main memory where contents of R1 plus this offset. Any questions? Sure. LDR is from main memory to register. This is the destination register. For STR is from register, our source register, to main memory. So for STR, we're going to change the content of main memory. For LDR, we're going to just read it from main memory, store it into register. So content of main memory stays the same. So for LDR, we need to identify location of the memory so that we can read and store into R0. How you find the address of main memory? Contents of R1 plus 12, this offset. In this case, we need to go mem2, put it into A. Let's say R7 is the A register you'll be given. Move 0 to R5, meaning just clean whatever it is in the R5, get rid of it. And then R5 plus some number, that's the memory location. Go get it, put it into R7, which is A. In C, when you say memory 2, that means memory array in 2. So this will tell us memory array 2, the whole 32-bit, we want to store A. Memory array 2, where is it? In the main memory, array 0 is the very bottom. Array 1 is here. Array 2 is here. And array 3, 4, 5. Each array is a 32-bit in the ARMS architecture. So when you say array, didn't say anything about the number of bits. But in the ARM, everything is a 32-bit. Make sense? But in C, it says array 2. Where is it? So that's 0, 1, and 2. In the ARM, we need to exactly tell the system that is the memory address of what? 8. So even though you see 2 here, this should be 8, not 2, not 3, not 4, not anything else. So in the ARM, when you are given, I said when you are given in the C code, only C code, when you are given in this instruction, you don't have to multiply this guy by 4. But when you are given in the C code and you need to access to the memory, then you need to multiply this guy times what? 4. This times 4. That's it. Why 4? Why not 2? Anybody? Exactly. One array, there are 4 bytes is a 32-bit. This is the big endian, but memory address is the first byte address. That's the whole memory address. Memory address is going to be 0, 4, 8, 6, 12, 16, and so on. So it has to be multiple of 4, the memory addresses. Let's say we have the same example. So in the quiz in the future, I said, I'll give you this guy, okay, contents of main memory, and then I'll give you R contents of R5, okay? R5 could be something else. And then this number, you should be able to find what is the value of R7 after we execute this instruction. Make sense? For store, we're gonna store the content of register into main memory. Therefore, we need to read R0 first. This is not our destination anymore, right? This is not destination. We need to read the contents of R0 store into main memory where contents of R1 plus this number will give us the exact memory address where we want to store. So let's say we have this guy. We want to store into 5. This is the register. We need to put the register value in here. What's the value of register in here? Which register we need to put it in here? R9, and then store into 5 times what? 4. 5 times 4 is what? 20. 20 is in hex, 1 and 4. Another example. So what are we doing in here? We clear R1, and what happened in here? We're going to move this guy into here. So after this, R9 is 42, and 42 is hexadecimal as a 2A, so just 42 or 2A. Now, store R9, R1, OX14. What are we doing here? What's the value of R1? 0. We did that. 0 plus OX14, which is 20. Now what do we do? Read R9. R9 is this guy, and we're going to store into here. R9 has OX2A, so those are the very bottom, okay, 1 byte. So after this guy, we end up getting this. So you can scratch out this, and this is the new content of memory. It doesn't matter which architecture you use. So this is the big endian, so it's going to go 2A here. If you're using little endian, same address, but location is going to be here. Let's say we have a 4 spot, and I ask you to write 19 and the decimal number. How are you going to write 19 in here? Can you write 19 and the later spot as a 0? Is it 19? No, it's 1900. So when you say 19, okay, in the 4 spot, that has to be here, and then any empty spot has to be 0 so that we can read as a 19. Same thing in the hexadecimal. So these guys automatically 0 because we want to store 2A, nothing but 2A. That's the only way we can do it. Good. If it's a negative number, I mean, it's a completely different story. Yeah, this one. Okay. So here are given. So these are given. Okay. This R1 and R9 given. And this contents of main memory is also given. Now the question is, after we execute str R9, R1, 0x14, what's going to happen in the main memory? Store, this is our source, so we need to read R9, which is OX2A. That's the step 1. And then we need to store into main memory where main memory uh, address of R1 plus OX14. Okay, those are the two steps for STR. We're going to read R9, store that into main memory where memory address R1 plus OX14. We're going to put this into where R1 is 0 plus OX14, and that is OX14, and that is 20. So now we know the address. I may give you the address as a hex, address as a decimal. You should really be careful. Either this is the hex or decimal number. How do you know the number is a hex? You're gonna see 0x. If you don't see 0x, that's a decimal. We're good so far? And where's the 20? It's a 20 right there. We have something in here, but we're gonna store that with a new value. It's gonna be OX2A or OX 1, 2, 3, 4, 1, 2, 2A. They are the same thing. So the accessing memory address of 2 times 4, 8, that should be memory address, and so on. Should be multiplied by 4. And then again, this is the last time we're going to look at the little endian and big endian. And if this is big endian, we're going to write this way. So that's the byte addresses, and then memory address is 048C. And little endian 048C, same, but the location of those bytes are kind of a little different. So when we use byte, LDR byte, that's byte 9. In this case, doesn't have to be multiple of 4, because as long as any number in the byte, we can get it. So in this case, byte 9 is right there. In this case, byte 9 is right there. So it really doesn't matter. Big endian, little endian, we're going to end up getting the right one. Just a matter of organizing those bytes is smaller to large or larger to smaller as a memory addresses. And we'll focus on mostly LDR and STR without byte in this class. So quickly, data processing instruction logic operations. We have AND, OR, XOR, bit clear, move, and NOT. So if you are given, it's on the slide, you don't have to copy this down. You are given R1 and R2. We want to AND them, AND them bit by bit. So for these are all AND, so we just need to copy this down, because 1 and 0 is a 0, 1 and 1 is 1. So in this case, you can copy that down. And then since 0 and something, that's 0, so everything is 0. Opposite way for OR, we just have anything you see 1, we're going to put it 1. And then copy these 2 bytes in here. XOR, if you recall, 312, XOR gates will do what? Check for the odd number of ones or even number of ones. If there are odd number of ones in the input of XOR, you're going to have 1. So we have 0, 1, and 1, 1, that's even, so 0, and so on. So in 312, we use this XOR into parity check, error detection, and then be clear. If the bit is 1, we're going to clear that up. Bit is 0, we're going to have that one. So the bit clear is just kind of the first one, R1, and not R2. It's the same effect. And then move, not move R2 to R7, but flip the bits. R2 to R7, flip the bit, 1 to 0, 0 to 1. And we'll need to talk about this, right? Just to giving you the idea, logical shift left, logical shift right, and we're gonna have some numbers. And again, R0, R3, R9, R8, they are our destination register. So the result is going to go into there. So here are some examples. Logically shift left by 7 bits of 0. Logically shift right by 17, 17 of 0. For the logical shift left or right, any empty spot, we put 0. However, arithmetic shift, when we shift, we need to look at the most significant bit and keep the sign. It was 1, we need to fill in 1s. If it was a 0, we fill in 0s. And then rotate 23 1 bits. So you push to the right, and then whatever left from the 32-bit, we feed it back to from the front. So it's a rotate. The register shift amount is this lower 8-bit. So when we have register and register, we're gonna just use 6 and take the lower 8-bit, and this much we're gonna doing the shift. And we have a R6, only lower 8-bit. Okay. Take that and use that to shift conditional execution. So we're gonna have some conditions because of that condition. So for example, if then statement, we are not going to execute every single instruction, right? Sometimes we need to skip. What's the condition for the flags? We talked about this and when we talk about the ALU. NZCV, those are the 4-bit for the conditions, and is the negative. If the result is the negative, n equals to 1. If the result is 0, then z equals to 1. When there's a carry, we're going to put c equals to 1. If there's an overflow, we're going to set v equals to 1. In the conditional execution, depends on what we want to know. We're going to use this 4-bit condition binary numbers in the instructions. So there's some signed and unsigned, and positive, negative, equal, not equal. We'll actually use this later. And those bit conditions are from here. Okay, ALU flag NZCV. So we talked about this. Based on this, we can detect the overflow, detect the carry, detect the negative, detect the 0. We can compare and set any of these different ways. And for our class, we're going to use CMP compare. Compare R5 and R6. When you have this instruction, what's going to happen is R5 minus R6. That's what we're going to do in the ALU in here. So when you have two registers, A and B, we're going to fit this in and you subtract, and based on the result, we're going to have multiple of ones in the flags. If we subtract that, it's a 0, z equals to 1. It's a negative, n equals to 1. Carry out, and c equals to 1. And signed overflow, v equals to 1. We really talk about all of those when we talk about the number systems. Copy this down. So we have an instruction, CMP R5 and R6. So compare contents of R5 and contents of R6. Then we have to do some actions, right? Depends on the result. And the first one was BHI. So the first letter is for the branch. Next two letters is going to be from the condition. So this handout, while I'm preparing for this lecture, I made this. So you will see as a first page, see data processing. In the data processing, first page, and we have an instruction, XOR sub, okay, add. If you move down, there is a shift, okay, move LSL, LSR, and ASR, all of those. Okay, there's a CMP as well, which is compare. So the first column that you see is a 4-digit binary number we call CMD. That's something we're going to use it later. And then if you flip it, you don't have to look at the format at this point. That's a little bit later one. If you flip the page, the top says of memory, so you see store and load. Okay, we'll focus on store and load. And in the middle, instructions that affects the condition flags. Do you see it? That's the AND, subtract, compare, shift. We're gonna talk about that a little bit later. And then we see branch. After branch, you see the conditional execution, and mnemonic says EQ, NI, CS, MI, right? And there's a COND value as a 100. We have HI. That's the HI, BHI, branch, unsigned, higher. Second number, we treat these two guys unsigned number. Second number higher than the first number, go 1. So if, let's say, R5 equals 1011 and R6 equals 1110, after we execute this, we compared content of these two unsigned number. Second number is a larger than the first number. So in this case, we need to go 1 and executing add R6, R5, R6, something like this. And then B, G, E. So now we need to look at GE. When we look at GE, signed greater than or equal. Then R5 is in decimal. So that is negative 0.101. That's the negative 5 for the R5. And this guy is 0.010 is the negative 2. R2 is greater than R5. So after this, we're going to go to subtract R6, R5, R6. I mean, I just made up these instructions. But the point is, the first letter is a branch. You need to look at the second two letters, see whether we actually take the branch or not. So if it's not, then we're going to execute the next one. Next line. If R5 is a 17, R9 is 23. In this case, it's a 17 minus 23 is a negative 6. So the negative flag is going to go up. And based on that, we'll do different actions. Yeah. Oh, the good point. So this is, I'm going to fix that. So B high is unsigned comparing two numbers, right? So this should be BEQ. So change that to BEQ, typo. And then second method, you're going to put S at the end, and then it's called set conditioning flag. So when we add these R2 and R3, R2 and R3, if the result is 0, negative, or overflow, and the carry happens, we're going to set any those flag up. Okay, so simply adding S. And then also we can put conditional ones, subtract if not equal to, or something like this. So these are the different ways to do it in the ARM instructions, but we're gonna just use for our class majorly CMP only. Branch instruction, up to this point, there's a conditional branch. Branch if equal, branch unsigned high, branch not equal. There's a condition, right? But there's no condition. Branch also using three letters. I'm gonna say branch always BAL. We're gonna use three letters BAL. And in your table, the last one, the conditional execution, last item, 1110, you have a two-letter AL, right? So that's the case. And there's also another called branch and link. We'll talk about that later if we have time. Copy this down. So we're gonna move decimal number 17 into R2. And the next instruction is branch always where you will get some target word. So we don't want to use this as a add, subtract, anything reserved for the instructions. We cannot use that. But as you saw in the previous, go 1, go 2, go 3, target here, there, and we can use anything. But once we hit this guy, there's no condition. It's unconditional branch. Once you hit this, you have to go. No choice. Where is the target? Target is here. You're going to execute this guy. Therefore, or R1, R1, OX4 is not going to be executed. Copy this down. So let's go through instruction by instruction. So we're going to move decimal number 4 into R0. After we execute this, R0 is going to be 4. And then we're going to add R0 plus R0 and put it back to R1. So now after this, R1 is going to be 8. Now compare R0 and R1. So what do we do here? Exactly. We're going to subtract. So R0 minus R1 is a negative. So we know it is a negative. And the flag n equals to 1. Now, this is the conditional branch. Branch if they are equal. If they are equal, it's branch. So if we want a branch, which flag should be 1? Right? Z. If Z equals to 1, then we're going to take this branch. Whenever we have a Z equals to 1, meaning what? The result is a 0. When we have the result is 0, then Z flag is going to be 1. But we have N equals to 1. Therefore, it's not going to take the branch. And we're going to execute R1 or 1. So R1, we have 8 which is 0000 all the way down, and last 4 bits of binary number is going to be 1000, and decimal number 1 is all 0 and 1, and we're going to OR them. So now our new value is going to be number 9, and then R1 plus 78, go put it back to R1. So our new R1 is going to be 87. So now we have if then else statement for loop while. Let's take a look at this if then statement. Copy this down. So you are given C code. If I equals to J, what we want to do, F equals to G plus H. If they are not the same, F equals to F minus I. And you are given R0 as an F, R1 as a G, R2 as a H, R3 I, R4 is J. So what do we do first? Which instruction we need to do first? CMP. And I is what? R3, J is R4, so CMP R3, R4. Then we want to test they are equal or not, right? So we need to use conditional branch B and which 2 letters? BQ or BNE. There's a 2 routes. You can use BEQ, but I use BNE. So if they are not equal, go 1, go 1. Because if they are equal, we add, but they are not equal, we need to subtract. So we have subtract. F is R0 minus R2. I should be R3. Okay, I'll fix it. This should be R3. F minus R3. We need to execute this. And then if they are not equal, we go there. But they are equal, we need to add. So right after this, if we are not taking this branch, we need to add G and H. G is R1. H is R2. So G plus H, you put it back to F, which is R0. Are we good? Are we done? If you just keep it this way, if it's not equal, we jump this and we can do subtraction, just like what we want to do. However, if they are equal, then we're going to execute this, add, and then we're going to execute this guy as well, but we don't want to. So we want to skip this line. How? Branch you always go to and go to is somewhere at the bottom so that we don't execute go 1.